Hello everybody, welcome to IB Buddy Grade 9 Mathematics. Today we're going to be looking at powers and scientific notation. So first, let's look at what are powers. So powers are a convenient way, aka like an easy way, to show repeated multiplication. So we'll get into that. So first, let's see the form. So the form of a power is first you have the base, and then you have the exponent. So here we have an example, 5 to the exponent 7. So this read as 5 to the exponent 7. So here, this is the base, right? And then that small number you see up top, that is the exponent. So altogether, this is read as 5 to the exponent 7. And this is the exponent, and this is the base. The big number is the base, the small number is the exponent. So exponential form is essentially just like this form, base and then the exponent. And then, so we have an example here, 3 to the exponent 4. So we have the base and then the exponent. And so the expanded form would be 3 times 3 times 3 times 3. And so if you didn't know already, brackets next to each other, as you can see here, there's brackets next to each other. When there's brackets next to each other and there's like nothing in between, that means that it's multiplying. So it's 3 times 3 times 3 times 3. And this is because this is the base, right? This is the number. So let's just say we have 3, right? Let's just, in our minds, remember 3. Now we have the number 4. So that 4 means that we multiply 3 4 times by itself. So we multiply 3 by 3 4 times. So 3 by 3, this is 2 times, 3 times, and then lastly 4 times. You see how it's being 3 is being multiplied by itself 4 times. So the exponent tells, so essentially the base tells us what is going to be multiplied by itself, and then the exponent tells us how many times it's going to be multiplied by itself. So if we evaluate 3 to the exponent 4, we get 81, because 3 times 3 times 3 times 3 equals 81. So powers with the base as a negative. All right, so let's look at that. So we have negative 5 to the power of 2. So how does that equal negative 25? Because wouldn't this just mean you'd have negative 5 times negative 5? Because remember, negative 5, you see, okay, that's the base. And then 2 is the exponent. Okay, so that means negative 5 should be multiplied unto itself 2 times, like this. And that would give you 25, because a negative and a negative equals a positive. But no, it doesn't work like that. So essentially, if you have a base with a negative, right? So essentially what it's saying is that we have 5 to the power of 2, right? But we're going to times it by negative 1. So this negative means this negative 1. It's like hidden. So when you're doing that, it's you first negative 1 times 5 to the power of 2. So this is essentially this, right? So this negative 1 represents this negative sign. So it's essentially saying that whatever 5 to the power of 2 is, we multiply that by negative 1. So we first do 5 to the power of 2, which is 25. And then we times it by negative 1, which would give us negative 25. So now you know that. Now you know how. So now we have this, we have negative 5 to the exponent 2 equals 25. But here, we see that the negative is in the brackets. So when the negative is in the brackets, it means it's directly affecting the base, right? So it's not like here there's no brackets, so the negative is sort of separate. But here, first, you see that it's in the brackets, so it's directly affecting the 5. Because if you know BEDMAS, right? Here, when we have negative, right? When we have negative, BEDMAS, we first do brackets, then exponents. So we first do exponents. So we do 5 to the power of 2, which is 25. And then BEDMAS, so brackets, exponents, we did that, which is 25. Division, multiplication. And then this negative is essentially is a secret -1. And it's timesing by 5. So this negative is like a -1, and it's being multiplied by 5. So multiplication comes after exponents. So you first do 5 to the power of 2 and then times that by the -1, which would give you -25. But here, the negative sign is inside the bracket. So that means we do brackets first, because in BEDMAS, B stands for brackets. So we do brackets first. So in the brackets, we see that -1 is being times by 5. So that means that we do -5 to the exponent 2. So then that would be like this. -5 times -5. Like that. And that would give you 25. Because negative and negative equals a positive. So that's why this and this have two different meanings and two different answers. Alright, so now let's recognize bases. So here, you can easily tell for number 1, the base is the big number, right? It's 3. Boom. The base is 3. Okay. But here, for the second example, we see -3 to the exponent 4. So here, remember we talked about this is not first, right? The negative isn't the -1, because you know this is a -1. The -1 isn't multiplying by 3 first. You first do exponents, because BEDMAS, you first do exponents, then multiplication. So this is not directly affecting 3, the base. So the base would still stay the same as 3. The base would still be 3. But here, in number 3, now it's in BEDMAS, we do brackets first, and in the brackets, we're multiplying, right? So that's the first thing we do. So it's directly affecting the 3, aka the base. So this is a part of the base. So that means that the base would be -3, because it's directly affecting the base. Whereas here, it's not first. First, you do exponent, then you times it by -1. But here, you first do times -1 by 3, and then you do the exponent. So it's directly affecting the base. Now let's get into scientific notation. So what is scientific notation? So it's a quick way to write large numbers. So how do we do it? So first, let's look at this example. We have this huge number, right? So we have 602 million. So how do we write this in scientific notation? So in scientific notation, you always want like a number, right? So let's just say like 7.2. And you times that by 10 to the power of like, I don't know, 4, 8, whatever you want. So that's how you usually do it. So how do we write in scientific notation for this? So first, always imagine an imaginary decimal place for a whole number. Like you see here, there is no decimal place. You can't see any decimal places. So always when you see no decimal places, always assume it's always on the far right. So to the all the way to the most right of the number. Always to the far right. So now you want to count how many times it takes you to go from here all the way to in front of the first number, right? So we recognize this is the first number. We want to take this decimal place and travel it all the way to in front, by the way, in front of the first number. So let's do this. So we do 1, 2, 3, 4, 5, 6, 7, 8. It takes us 8 times to get the decimal from here all the way to in front of the first number. So that means that we already know. We just write times 10 to the power of how many times the decimal place went to go to in front of the first number. So in this case, it was 8 times. So we write 10 to the power of 8. And then you look at the number here. So here we see that the number is 6.02. And like the numbers after, they don't matter. So you see how when we put the decimal place here, this is the number that it becomes, 6.02. So you place that 6.02 into here. And this is how you get it in scientific notation. So you first write times 10 real quick, and then to get the power, the exponent, you want to count how many decimal places it takes to go from wherever you're at to the front of the first number. And then after that, whatever that number becomes, you place that in the first part. And there you go. That is scientific notation. Because as you can see now, this 6.02 times 10 to the exponent 8, right? 10 will be multiplied onto this number 8 times. So this means that 10 will be multiplied unto itself 8 times. And you know, when you multiply something by 10, especially when it has like a decimal place, right? And you multiply it by 10, every factor of 10, it goes to the right 1 decimal place, right? So if we times this by 100, which is 2 tens, it should go 1 and then 2 right there. And 2 tens, which is like this, 10 times 10, like that, right? That's essentially 10 to the power of 2. So if we did that 8 times, right? This means that the decimal place will go 8 times to the right. So 1, 2, 3, 4, 5, 6, 7, 8. And it'll return to its original form, which is this. So this is essentially shortening the number. And it's very easy to write. All right, now let's go with a number that is smaller. And you can see it's decimal. You see the decimal places over here. So you want to now, because this is a very small number, so you want to make it a little bigger so you don't have all these zeros and everything. You only have the important numbers, which is 4, 2, and 8. So what you do is first, obviously, write the times 10. And then look at the decimal place and go in front of the first number, right? So the first number you see. So we go 1, 2, 3, 4. Because you want the decimal place to be in front of a number so that it is only one number, right? It's not like the decimal place goes here, and that creates two numbers, 4 and 2. You only want it to go to one number. So the first number you see here, you just place it in front, and now you have one number, right? And then all the rest of the numbers are on the right of the decimal place. So now you count how many times did it take to get here. So you see 1, 2, 3, 4. So that means that we put to the exponent 4. And then you look at the number and see what number you created. So here you see the decimal place is here. So this means it's 4.28. So you just get this number and place it over here, 4.28. And this is your scientific notation. You think this is over, right? It isn't. Because if you've noticed, if we have just 10 to the power of 4, decimal place would go like this, right? And make the number larger. Because if we did it like that, it would be like this. We had 4.28, and then we go 1, 2, 3, 4. And then every blank space is 1. It is 0. So it would go like this. So then the number would be way bigger than it was. It's not the same value. So this is because we used a positive exponent, which means that the decimal place will go to the right and make the number bigger. But we want the number smaller because this number is small. So what we do is we actually put a -4 on the exponent. Yep. So the -4 essentially symbolizes that you want the decimal place to go left 4 times. So then when you go left 4 times, it goes 1, 2, 3, 4. And then that's the decimal place. And so these empty spaces are zeros. So then you just write 0, 0, 0. And then if you see that to the left of the decimal place, there's no number, then you write 0. Boom. So now you got your number, which is 0.000428, which is the same as this. So that's essentially what you do. So you just, for numbers that are small, you place a negative exponent so you can make the numbers more simple. So essentially, if you have a number that's big, right, and it doesn't have a decimal place, you make the exponent positive, and when the decimal point, this decimal point, goes from here and then goes to the left, that's a positive exponent. But when the decimal place goes to the right, that becomes a negative exponent, right? So let's do another example. Let's just say we have 0.00085567, right? So if we have this number, we want to write it in scientific notation. We first write times 10. And now let's find the exponent. So we see that we need this decimal place, and we want to make this number a little bigger so we can simplify it. Because we don't want all these zeros, right? We just want the actual numbers. So if we move this decimal place 1, 2, 3, 4 times, you see we placed it in front of the first number we saw. And there's only one number before the decimal place. We moved it 1, 2, 3, 4 times. So that means that we put a 4 on the exponent. And since we went from move the decimal place to the right, that means that we place a negative on the exponent. And then look at the number that you created. So the decimal place would be right here. So that would be 8.567. And so you just write that on the left of the scientific notation, 8.567. And that is your scientific notation. And then if we had 490,000, right? So we see there's no decimal place, so we automatically assume there's a decimal place on the far right of the number. Do the times 10, and then to find the exponent, we first count the decimal places. So 1, 2, 3, 4, 5. Boom. You have that decimal place, and you see that there's only one number before the decimal place, and that's 4 here. And so we moved a total of 1, 2, 3, 4, 5 times. So that means the exponent will be 5. And to check if the exponent will be negative or positive, we see that it's going from here all the way to the left. So it's going left. So when it's going left, it means that it's positive. So then you just look at the number you created, 4.9. 4.9. And boom, you've created your scientific notation for this number. Now, let's do scientific notation to standard form. So we have 3.25 times 10 to the exponent 9. So what we do first is we look at this number, right? And we look at where the decimal place is. Oh, the decimal place is right over here. So we see that it's a positive exponent. So that means that we have to move this 9 places to the right, because positive means making the number bigger. And when you're moving the decimal place here, you're making the number bigger. So from 3.25, you're making it 32.5 if you just times it by 10. So every time you're timesing it by 10, it's getting bigger and bigger and bigger. 3.25. Let's move this decimal place 9 times. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the decimal place is here. And each blank space is 1 0. So 0, 0, 0, 0, 0, 0, 0. And boom, you got your number, which is really huge. This would be your expanded form. All right, now we have 4 times 10 to the power of -4, let's say. So with this, what we first do is we see that it's a negative exponent. So it means that we're going to be moving left, because you remember, when it's negative, you go left. When it's positive, you go right. So with this, we just grab 4.0. And so we go 4 places to the left because of the exponent. So 1, 2, 3, 4. So the decimal place is here. And so the empty spaces are zeros. So you just write 0, 0, 0. And you see there's nothing before the decimal place. So you also write another 0. So this would become your number, 0.0004. That's your number. Because the 0 after that, it doesn't really matter. It's nothing. So you just exclude that, and it becomes 0.0004. That's your expanded form. So thank you for choosing IB Buddy. This is grade 9 mathematics. You've learned what are powers. You've learned how to identify the base and exponential form, expanded form, how to evaluate powers, powers with the base as a negative, how to do scientific notation, and scientific notation to standard form, aka expanded form. Thank you, and I'll see you tomorrow.